Hi, everyone, and thank you for joining us today for our Johns Manville Energy Saving Techniques webinar. I'm Natalie Kearney, and I will be your moderator for today's presentation. Before we begin, I would like to go over a few logistics. If you have any questions or concerns throughout the webinar, you may submit them at any point during the presentation via the Q&A or chat feature at the bottom of your screen. We will address these questions live at the end of the presentation. Also, just a quick disclaimer, the information provided in this webinar is to not be used as a substitute for professional engineering design and/or documents required by a building code, contract, or law. Please refer to the manufacturer's specific application guides. Additionally, we will follow the webinar today with a survey. This is your opportunity to provide us with feedback on how we did today, ask any additional questions you may have about the topic of the webinar, or suggest new topics for webinars you'd like to hear in the future. Now with that, we'll dive into an introduction, and I will hand this over to JR.
Thanks very much, Natalie. Welcome, everyone. Good afternoon or good morning, depending on where you are. Thanks for joining us today. I'm excited to dig into today's topic. My name's JR Babineau. I'm our research manager of building sciences here at Johns Manville. I've been with JM for 27 years. Over that time, I've worked on a lot of different things. Currently, very involved in a lot of industry and government groups, as well as product development and research that we do here at JM. And so I thought today's topic was pretty interesting, that this is a specific request from folks. And oftentimes, we go more into the nuts and bolts of things. But today, energy saving techniques for buildings, we're going to be a little more high level, I would say, So we're going to first talk about, just why is energy efficiency and reducing carbon emissions important for buildings? And let me just kind of preface, a lot of the focus that I'm going to put today is on building energy efficiency, but I would argue that is the first step in reducing building carbon emissions, We can take other approaches to reduce emissions, but if the building is using efficiency poorly, we've kind of really done things in the wrong order. So we're going to be looking at, why is this important? We're going to, again, from a high level, look at how do buildings use energy. And we're going to look at both residential and commercial buildings. We're going to look at new construction and existing buildings. So we're going to cover a lot of ground. We're going to look at these different energy saving measures. Again, dig in a little bit to how to apply them, and then talk about some takeaways and resources. Keep wanting to hit my button. There we go. All right, so first, why is this important? So the graph that we've got here on the slide, shows using 2022 data, kind of how the United States used energy overall, our entire economy, from the fuels to electricity to then end-use sector. And if we look over on the right, the bottom two boxes are residential and commercial buildings, So those two combined account for about 29% of the overall electricity use in the United States. And maybe even more importantly, buildings account for 74%, so almost 3/4 of all electricity used in the United States, And so that's really the big, why is this important, Buildings use a considerable amount of the energy, that we consume here in the US and also in Canada. So, because building energy use is a big piece, building codes, include energy, as one of these regulated aspects of buildings, along with things like structural, fire safety, and other elements in building codes. And so the maps on this slide show energy code adoption at the state level in the US, with the residential code on the left, commercial on the right. And you can kind of see the legends are a little small, but basically as we go from orange as being kind of the most older or out of date codes being enforced to light green and then dark green, right, as being the most current codes. We can see on the residential side, currently 27 states in the US have a residential code that is no better than what was published all the way back in 2009. And so just for comparison, right, a home, like the same home built to the 2021 code, which is the most current version, will be 20 to 30% more efficient than that exact same home built to this 2009 code, right? So if we compared a home built in Washington State to a home built in Iowa, let's say, just right, pulling a couple places at random, right? Same home, the one in Washington State will be 20 to 30% more efficient. On the right, we can see, right, there's a lot more green and a lot more dark green, which shows us that we're a little bit better actually when it comes to adopting and enforcing building codes for commercial buildings in the US. Kind of shifting gears, looking for our friends up in Canada, right? They also use energy codes to help manage and reduce the energy consumed by their buildings. Back in 2020, Canada actually adopted a new set of building codes that introduced this kind of tiered approach with the idea to have provinces, as they adopt and update their codes, steadily reduce building energy use. And so, right, the map here really shows, at least a couple of weeks ago when I made this map, kind of what the status was of building codes in Canada. So we can see that the dark gray ones kind of had no real adoption information kind of published. So I have to assume they're just on whatever their current provincial code is. The light gray, so Ontario and Quebec and New Brunswick, those provinces have kind of announced that they are currently remaining on their current provincial codes, which are kind of, from what I understand, pretty similar to this tier 1 of the current Canadian code. The dark blue, right, these kind of bright blue provinces, right, Yukon, Alberta, Manitoba, they have all adopted basically the tier 1, this initial tier of the 2020 code. Saskatchewan in particular has adopted tier 2, so a slightly better version of the code for homes, and tier 1 for commercial buildings. So that's why I striped it. And then finally, kind of the most advanced building code right now in effect in Canada is in British Columbia, where they were really kind of ahead of the game, even in terms of these tiered codes, where they have what they call a step code. And they are already on step 4 of, I think, 5 of their code progression. So new buildings in BC are definitely leading the way in terms of energy efficiency as that goes. So, right, we kind of talked about why is this important, right? What's really kind of driving, driving this energy, the drive to energy efficiency in buildings. And so let's kind of look at how buildings use energy. And this, because we're talking about this at a high level, one of the key things we get to dust off is this old kind of building science adage that's been around for decades now, right? That buildings are systems of systems, right? That's a really important thing, right? We can't just change aspects of buildings without taking into account how other things get impacted. And we need to remember that buildings are much more complicated, right? They've gotten a lot more complicated over the years, especially in the last century or so, right? And so the images on the slide actually show, right, this kind of a progression of 1,000 years of building history for the human race, where on the left-hand side, we've got 1,000-year-old church in Ireland, right? It's just made out of dry stacked stones, right? There's no mortar, there's no anything, right? Obviously, very efficient because it doesn't use energy at all, right? Very cold on a winter's day, very durable, right? But not a very comfortable place to be in, right? And as we move across the slide, we kind of see a progression of how we construct buildings from, brick and mortar to, wood framing to, on the right-hand side, right, combinations of concrete and steel infill and a bunch of other layers. So, right, we need to recognize as we look at these questions we're going to talk about today, right, that buildings have gotten just a lot more complicated. And of course, we've got all these interconnected systems, right? We've got the building envelope, we've got heating and cooling systems, we've got hot water systems, lighting systems, sometimes other processes, right? And these things all impact each other. And that'll be a really important thing to keep in the back of our minds as we go through today's presentation. All right, so, right, how do buildings use energy? So we kind of set the stage. Let's start digging in a little bit. We're going to start with residential buildings. And right, the first thing we're going to look at is homes. So this is data from 2020 from the US to start. We'll look at Canada again here in a second, right? But if we, the graph has got a lot of bars on it, but if we just look at the top one, right, that's all homes. That's kind of everything lumped together, single family, multifamily, mobile homes, right? All of those things together, we see, right, that right away, space heating, right, is the number one energy use, 42%. Right, followed actually by other, right, which would be appliances and other things, and then hot water. If we actually add air conditioning, right, which is that light blue bar at 9%, we see that heating and cooling makes up 51% of all the energy used by our homes. And so, right, if we really want to make a big dent in that energy use overall, that's obviously going to be a good first place to start. Just kind of for historical perspective, the pie chart on the right is showing the same sort of data, but from back in 2011, right? And so we see that it hasn't really changed a lot, right? Water heating is still at 18%. Space heating, right, has come down a little, right, from 45 to 42, but not much. Air conditioning still sitting at 9%. So in terms of the percentages, we're pretty much where we were 13 years ago or so. Kind of shifting gears for a second, looking again up at Canada. Obviously, space, this is from 2019 data. Space heating, as you would imagine, is a little bit higher, right, for homes in Canada because they are in general in a colder climate than lots of the US is. Right, and air conditioning at 2% is obviously much lower. But again, water heating, right in there in the teens. So, what this tells us is that, right, the same sort of measures that we might talk about for homes in the States are going to be equally applicable to saving energy in buildings and homes in Canada. Pivoting over to commercial buildings for a second. Right, again, so we've got data here for commercial buildings in the US from 2018. That's kind of a while ago, but that's the most recent real good survey of commercial building energy use that we have. But again, lumping all commercial buildings together, right, new and existing, we see space heating again jumps out, right, as the single biggest component. But of course, commercial buildings have got a lot more variety in size and shape and use than we see for homes, right? So that's where we get these other pie wedges, right? We get things like ventilation at 11%, 7% for things like cooking, 10% for features like lighting, right? So a little bit more of a mix when we look at commercial buildings. And again, similarly, again in Canada, where we've got 2019 data. And again, space heating, the single biggest piece, water heating at 6%, space cooling at 5%, lighting, again, right at 13%, that's a big piece. And again, some of these pie, the wedges that we see for the Canadian data versus the US data really just boils down to how are we lumping this data together, right? Things like auxiliary equipment for Canada, would equate to some other different of the wedges that we see on the US slide. So, again, in terms of where the big things that we could go after, clearly space heating, lighting, ventilation, right, become a lot of the things we can go after for saving energy again. Okay, so now, right, we've looked at how buildings use energy. So we kind of know where the big targets are. So let's, dig in a little bit more and talk about, right, where do we really find the savings, right? So from the graphs we just looked at, we know for residential buildings, it's going to be heating and cooling, it's going to be hot water, and after that, it's going to be that other, right? So appliances, plug loads. So we're gonna dig into that. And then on the commercial side, again, heating and cooling, right? Ventilation, lighting, followed by hot water. So we're going to touch on all of those things today. So first off, jumping right in for heating and cooling for houses, right? If we want to save how much energy we use for heating and cooling in houses, we need to understand, what parts of the house are driving those heating and cooling loads. So the graphs that we have on the slide kind of tell that story. Goodness, sorry. My computer wanted to restart, so we postponed that. I don't think we need that right now. So, right, looking at what drives these heating and cooling loads in our houses. And so if we look at, right, so left column is cooling, center is heating, right is overall, we see right away, right, air infiltration, which would be air leakage, right? That's a huge role, as does the heat that we lose or gain through our walls, right? That's the light blue. Through our floors, that's the dark green. Our roofs, that would be the light green bars. And then windows, right, for heating and overall, that's that light orange. And then ductwork, right, that's the darker orange. So right away, well, and then actually solar gain through windows, that's the light gray. So I've kind of covered a lot of pieces, right? But a lot of that is in the building envelope, right? Walls, roofs, floors and slabs, windows. If we kind of lump those pieces together, right, again, that's a big chunk of the heating and cooling load on our houses. Of course, HVAC systems, right, our heating and cooling systems also play a big role. We're going to touch on those two just a little bit. But first, right, we're gonna start with the big things first, right? With air leakage clearly being the biggest single factor, let's look at the benefits of air sealing. So, right, the best opportunity to prevent air leaks is in new construction when the home is built, right? And the list on the left side of the slide are the big holes, the really critical holes that it's important to have sealed, both from an energy perspective and to protect the indoor air quality of the house. So first off, right, ceiling penetrations, our homes have got a ton of holes in the ceilings, whether that's light fixtures or even holes that we might not always see because they're buried in the walls, things like plumbing vent stacks and the flue for your water heater or your furnace, right? All of these things require holes that go up to the ceiling and roof. Those holes all need to be sealed off. Things like cantilevers and attic knee walls, tubs and showers, attached porches, right? These all create a bunch of large, potentially really large holes in our walls that, again, need to be blocked off, need to be sealed. The best opportunity to do that is when the home is being built. Trying to do that after the fact, much more difficult. And then finally, garage walls, right? Many of us have attached garages to our homes. There's a common wall there. Those walls are often very leaky. And not only is that bad from an energy perspective, right, but that means that the house itself will end up sucking on the garage and sucking in all the junk, right? Car exhaust, fumes from the gas can for our lawnmower, cans of paint, fertilizer, you name it, whatever we have stored out in the garage, right? We're kind of drawing that all into the house. So it's really important that we air seal that off. And then from just from an energy saving perspective, that's the table on the right-hand side of the slide. So if we, again, thinking about new construction as our starting point, kind of taking a very poor starting point maybe at 7 air changes per hour. So that's what that ACH 50 kind of acronym stands for. It's basically saying that when we run a test on this house, it's leaky enough that every hour we're able to pull, change the air in that house 7 times. That's our baseline. That's not very airtight. But if we tighten that down then to 5 air changes per hour, we can realize about a 6% energy savings, right? That's pretty significant because that's overall not just heating and cooling energy. If we tighten it down again to 3 air changes per hour, again compared to baseline, we get another 4%, right? So let me take that back, right? That's incremental between as we march our way down. So what we see for one is that as we make this house tighter and tighter, right, the benefit that we gets smaller and smaller, right? Our first change is 6%. Our next change, right, another 2 air changes is only 2, right? We tighten it down again, we only get about 1% more savings. And so this is a common theme. If anybody has ever seen webinars or other education on energy efficiency, right, the better you get, the harder it is to get more savings. So something that we will definitely see as we go through. It definitely just happens as we make our buildings better. And also one thing to keep in mind, the savings that I've got here are from some energy calculations that I did right on a typical new home in kind of the Atlanta area, so climate zone 3. If we were to put that same house in a colder climate like Minnesota, we might see these numbers be a little bit higher just because of the cold climate effect, right? More energy being used for heating and air leakage becomes more important. So, all right, because, right, over 50% of a home's heating load ends up coming directly through the walls, the roof, and the floor, and because Johns Manville makes insulation, we're going to look a little bit more closely right at the building envelope and some examples of how adjusting the amount of insulation that we put into our homes, both in the walls and the roof, can help, and also how these things, right, impact differently. So, right, again, looking at this 2,400 square foot, right, quote, typical home, that's kind of the average size house currently built in the US, right, about 20% window area. We are going to look at a couple of different variations of this house, right? I'm going to look at a 2-story variation and a ranch variation because that's going to help kind of highlight to us how, right, changing the insulation amounts in the attic versus the walls has a difference, right? And you can imagine it will as we have more attic or more wall, right, in the various pieces. So, right, like the air leakage example we had before, these percentages that I'm showing in the tables are overall energy savings, right? Not just heating and cooling savings. And again, my baseline is, not very aggressive, right? So my baseline insulation in my walls is R13, which is probably what we're seeing pretty much anywhere throughout the country, even in states with a pretty old energy code. And again, attic insulation R value starting point is R30. So again, not super aggressive. So if we look on the wall side of things, right, we see that if we, keep our house framed with just 2x4s and upgrade our insulation in the walls to R15, we don't really get much improvement, right? That's not a lot. But as soon as we change our wall framing up to 2x6s, right, and we can put in R19 or R21 or R23 in those walls, we get a pretty good improvement, right? We're seeing, 5, 6, 7% improvement if we bump up our wall framing. Admittedly, there are costs associated with that, but we do realize pretty good energy savings. The other piece that really can help boost energy performance of a house is these bottom 2 rows on the walls table, right? This +3, +5 CI means we're adding foam sheathing to the outside of these walls, right? So again, keeping it as a 2x4 framed wall, but adding just R3 foam sheathing, that's only half an inch of foam sheathing, or R5 is just 3/4 of an inch. So we're not adding a ton to the wall thickness, but again, we can definitely, just by itself, we can see good improvements. And I just wanted to highlight, right, I'm showing a range on all of these tables. For the wall table, the higher number would be for a 2-story home, right, because more wall. The lower number would be for a ranch. If we look over at the attic side of things, again, as we increase our attic R value, how much insulation is going into the attic, see, we don't see as much, right? And that's really because the heat, the heat and the cooling loads that we get through our roofs is less, right? Than, even though heat rises and all of that, right? Even in a ranch home, right? We just don't see as much impact from boosting the insulation in our attic. Now, it's not to say that's still not important, right? When we take everything all together, we'll see in a minute that that's actually quite valuable. But by itself, we only see a few percent change by boosting up those insulation R values. All right, so talked about homes and new construction. Let's start kind of pulling this all together. Right, so new construction, right? Increasing the insulation and air sealing, right, in our homes for new construction can help quite a bit, right? Especially if we get it up to current codes. We see on the slide that I'm saying up to 20% savings, right? Just from insulation. And you might be saying, JR, you just showed me 1 second ago tables where we only save 6 and 7% or 3% from attic insulation. And I would say, yes, that's true. Right? But if we take the building envelope as a whole and boost everything up by a bit, then we actually get these savings, right, that are more than just those individual components, right? Those things, when we do it all together, instead of trading off bits and pieces against themselves, we get better performance. Remember, we saw that air sealing just all by itself can give us 6%. Again, when we bundle air sealing together with better insulation, we get even more energy savings. Upgrading windows, especially in new construction, is a great way to improve the envelope, especially since most double pane windows, they're only R3, R3.5, right in there. They're quite literally big holes in our walls. Upgrading to triple pane units, which usually have R values of more like 4 or even 5, right, can really make a big improvement. Right, this kind of 7 to 16%, right? So again, we can start lumping these things all together and we get good improvements. Looking at our systems, right? If we can change the efficiency and even type of heating and cooling systems that we have, we can realize savings anywhere from 6 to 25%. So a lot, right? So savings there on par with what we get from improving the insulation and air sealing. And the important thing to remember there, right, is that these things all work together, right? The better our envelope is, not only can we do a more efficient heating and cooling system, but it can be smaller. Similarly, right, water heating, we can get savings from anywhere from 2 to 11% overall just from changing our water heating. And that's can be either, improving the efficiency of the water heater, like going to a tankless or a higher efficiency tank water heater, or kind of at the extreme end, going to something like a heat pump water heater, which can be extremely efficient. Right, so all of these measures taken together, right, really, that's what brings the performance of a new home, to be, really as good as it can be. And I got to make my plug, right, but that the envelope, especially for homes, it's kind of forever, right? We don't tend to change those things very much, even though we change out our heating and cooling equipment as it reaches the end of its life. So those investments in envelope are really, beneficial. Similarly, for existing buildings, right, and again, right, existing buildings account for 99% of all homes already exist, right? We only add about 1% every year in new construction. So, that's obviously the big bucket of buildings to deal with. Again, it's the same things. Air sealing and insulation, right, can save us anywhere from 5 to 30%. 10% tends to be kind of the average. Right, but again, not only do we save energy, right, it makes a dramatic improvement in the comfort of our homes. Window replacements, right, whenever that needs to happen, replacing our windows, upgrading those to double pane Energy Star windows, or better yet, triple pane, can realize good savings. Just adding things like storm windows can save a bunch off of the heat loss through our windows. Kind of turning to the system side of things, right? Programmable thermostats. We've all kind of by now, I'm sure, heard about the benefits of programmable thermostats, and those savings are real, right? If we can set back our heating and cooling set points for 8+ hours at a time, right, we get a savings of about 2% per degree. 10% a year is pretty typical, right? So that means at night when we're sleeping, right, especially in the wintertime, if we let the house run a little bit cooler, especially then conversely in the summertime when we're running air conditioning, if nobody's going to be home in the home, right, in the house, if everybody's off at school and at work, letting that house run a little warmer when nobody's there, those things truly, represent some real savings. Similarly on our water heaters. If we can turn down how hot we're having our water heater heat the water up to, again, every 10 degrees can save us about 3 to 5%. And then finally, right, that big other category, appliances, right? If we can replace our washers, our dryers, our dishwashers, our stoves, right, when those things need to get replaced, if they're not already Energy Star rated units, replacing them with Energy Star rated units not only still gives us a really good appliance, but can reduce those energy impacts quite a bit. All right, how are we doing? You're doing okay. We're going to turn our attention now to commercial buildings for a minute. And, as you might imagine, the enormous variety that commercial buildings come in presents some complexities, right, in how best to save energy. Right, and some of the biggest challenges just come from the different size and shape that commercial buildings come in. So looking at the slide, right, the big, commercial buildings have zones, right? There's kind of this perimeter zone, right, that's usually about, 12 to 25 feet deep, right, and is basically attached to, right, connected to the envelope of the building. The heating and cooling loads in the perimeter zone do really get dominated by, right, the building envelope itself and the climate the building is in. But then there's this core section, the middle of a commercial building. That tends to get dominated more by, how the building is used and how large that core space is. And the climate that the building is in ends up becoming almost irrelevant. So let me show some examples of what I mean by that here on the next slide. So what we have here, right, are some sketches of the prototype buildings that the Department of Energy uses, right, when they are evaluating the commercial building code. So going across the top, right, we see something like a school, right? We can see there's a lot of complexity there. There's a lot of building envelope, right? A small office, which frankly looks a lot like a house. All right, or buildings like a small hotel or a small apartment building. Again, there's a lot of building envelope. There's not a lot of core, right? How these buildings are heated and cooled really gets driven, by the climate that they're in and the building envelope. Going down to the middle row, right, we see things like a warehouse or a strip mall. Right, and I feel like these buildings end up being a little bit more in the middle, right? We might look at these and say, well, there's a lot of building envelope there, and I would agree with you, but there can also be a lot of, think about a warehouse, there's kind of a lot of core as well. Or if we think about a strip mall, right, each individual bays in a strip mall might have a lot of building envelope, but if one of these stores is a retail store, right? It's going to be using energy or be heating and cooled in a very different way than if there's a restaurant right next door, right? So we can imagine how these different uses really drive the energy use and the heating and cooling. And then finally, if we look at like the medium office, the large office, the healthcare building, right? These buildings, while they still have a perimeter zone, they have really large core zones that, again, the heating and cooling in those areas, right, don't, they almost don't matter, right, what the building envelope is doing to what happens in the core. And we'll look at that in a little more closely here in a second. So, right, just looking first at all commercial buildings lumped together, right, we see that the drivers for heating and cooling loads end up being similar to what we saw for houses, even though we've got these core elements, right? But if we look first at heating, right, we've got windows, walls, roofs, infiltration being that kind of rust orange wedge, that's air leakage. Outdoor air, right, that's ventilation, so that's the 11%, right? But those dominate how much heating we have to put into the building, right? The wedges in both of these graphs that I've got kind of grayed and cross-hatched out, right? Those actually are helping, right? If we think about lights and solar gain in a commercial building, those actually reduce the heating load. So we're not, kind of getting into that much, but the wedges that are colors are areas where the heating system has to make that amount up. On the cooling side, right, we see right away lighting and solar gains, right, really drive how much air conditioning our commercial buildings need, right, followed by things like equipment and people. Right, those things aren't too surprising, but again, good to kind of acknowledge how big those are. But what's important, right, this is all commercial buildings lumped together. But if we dig in even just a little, right, and look at a few different building types, again, now we see all kinds of differences, right, that really steer us in different directions for saving energy, right? First off, if we look at a school, right, and my pie chart here is just looking at heating loads for this school, and I'm doing that because the heating load for the school is 3 times the cooling load, right? So if I want to save energy at this school, reducing my heating loads is like the place I should go first. And again, we see really similar to a house, right? Infiltration, air leakage, single biggest wedge on here, right? Followed by walls, windows, roofs, right? Those are our building envelope elements. And then outdoor air, again, that's the ventilation piece. So, right, we see right away, kind of what we would want to tackle if we wanted to help out the school. Totally different situation though if we look at a hospital or a large office building. For the hospital, actually the cooling load is about 30 times larger than the heating load, right? And we see right away it's dominated by just the equipment that's in that hospital and lights. Right, so if we want to reduce the energy use of this hospital, right, we're going to be doing some wildly different things than what we would be doing for the school. Similarly, for this large office building, again, the cooling load for this building is about 10 times larger than the heating load, right? But now, again, dominated by lighting and much even more so by solar gain, right? Not so much the equipment. So, the size and the complexity of the systems is really important. And again, getting back to this issue of perimeter zones versus core zones, right? It is not uncommon in commercial buildings, especially large ones like hospitals and large offices, for both heating and cooling to be called for simultaneously in different parts of the same building, right? We could easily imagine how in a hospital or in a big office, right, the rooms that are out on the perimeter right next to the windows, right, in the wintertime, they're going to be calling for heat, right? But the rooms in the center of the building, like an operating room or a computer server room, right, those are going to probably need air conditioning year round. So those sorts of complexities really, drive a lot of some of the things we do to help save energy in commercial buildings. And I am noticing that well, we're getting close. We're gonna get through this here in the next 5 to 10. So, right, heating and cooling for commercial buildings, right? If we're talking about new construction and looking at envelope improvements, really, I mean, the best thing that we can do is build to the most current commercial code. In the US, that's ASHRAE 90.1, the 2022 version, right? But if we compare that versus kind of one of the older versions, 2007, that's still in use, right? Walls have improved up to 32%, roofs have improved up to 33%, right? We really see that we just build to the current code or even a little bit better, we can realize a lot of good savings in new commercial construction. And so just to kind of highlight that a little bit more, I've got an example, right, of, again, a new construction. This is kind of a medium-sized apartment building, right, that was done in Vermont a few years ago, where they really took this seriously, right? They upgraded the insulation in the walls and the roof, right, a bunch, up to R36, R80 in the roof. That's a lot of insulation, right? They upgraded the windows, right, from, you know, a little better than R2 to almost R5, R4.5. Air leakage, again, was tightened considerably. And by doing this, all those things taken together, right, just from the building envelope, right, they saw big improvements, right? 40% savings, better than code by taking these measures all together. One final thing I wanted to touch on for new, you know, kind of new construction for commercial buildings is something called cool roofs. We've probably heard about this, depending on where you live, right? What this really means is a white roof. And a white roof just means that it's both highly reflective in terms of bouncing back the sun's energy into the sky, and also highly emissive. And emissive just means what heat, what energy that roof membrane is able to absorb, it can shed that heat very efficiently. And that's, you know, a white roof that ends up becoming better, certainly better than a black roof or a dark roof, right, which tends to absorb a lot and also emit a lot, or a metallic roof, which you know, reflects a lot of heat back, but what it does absorb, it has a hard time getting rid of. And if we go with a white roof, right, we reduce the roof surface by over 30 degrees, and we can reduce our air conditioning load by up to 20%. So, right, for especially like large warehouses, right, things with a large roof, that becomes a real good benefit. Oh, sorry, I forgot to add this, right? And we can actually see those similar savings in our building by adding another about R10 of roof insulation. But again, combining the white roof with insulation ends up being an even more effective strategy. So, right, finally, new construction, right, for commercial buildings, right, the energy savings, again, look similar to houses, right? One thing that we can often do with commercial buildings, right, in addition to just like the passive things like air sealing and insulation and windows, is even just the building shape and orientation, right? So while the building is still literally a drawing on paper, right, the choices that designers can make can really impact how that building will use energy. And that's kind of, right, when it's still just a drawing, that's the cheapest time to make a change. Again, these passive measures that we've talked about, right, air sealing, insulation, windows, cool roofs are really important. And then finally, right, efficiency of things like our ventilation and heating and cooling systems, our lighting, our control systems, right, those all make a big improvement. Similarly, similar to homes, right, for retrofit, you know, the vast majority of commercial buildings already exist. So, you know, those are a lot of areas that need improvement. And again, here's where, right, things like controls, right, can improve up to 20%, right? That's kind of even more than what we get in houses. And again, this ties back to this issue where so often commercial buildings, we're like heating and cooling simultaneously, and that wastes a lot of energy. And the more we can reduce how much that happens, the better. Again, air sealing commercial buildings are notoriously extremely leaky. The better we can air seal those building envelopes, the better it is. Roof insulation in particular and cool roofs become something that is an opportunity for retrofits, because commercial buildings do tend to get their roofs replaced on a pretty regular schedule, much more than replacing things like windows. One key piece I did want to point out, right, that's tied to HVAC systems, commercial buildings use a lot of hot water and steam and chilled water, right? Not just for cooking and drinking, right, but for lots of other things. The more we can insulate those pipes in commercial buildings, we definitely realize good savings from that as well. And of course, right, if we can bundle these things all together, right, you know, there's been a ton of studies out there that show we can see savings, right, of 15 to over 50%, right, when we do that. And here we're getting into just the last couple of slides. So, right, as we look forward, obviously, codes continue pushing us all towards making our new buildings be ever closer to being net zero energy, net zero emissions, right? There's a lot of places with those sorts of goals. Programs, right, beyond code programs like Energy Star and Zero Energy Ready Home are doing the same thing. So I don't think we're to see those things go backwards. When it comes to existing buildings, the map on the slide shows where, right, there's a lot of there's a lot of jurisdictions out there that are really starting to target existing commercial buildings, right? Commercial is the important word here, right? Where they are first usually requiring building owners to report energy use for large commercial buildings, and then after a few years of doing that, they follow on with what are called building performance standards, which are going to building owners and saying, now you must make improvements to these commercial buildings, right? We're not waiting necessarily until, you know, the building gets knocked down or whatever. We're saying, hey, these buildings are going to be around for a while. We need to address this. And I would expect as we look forward, we will see more and more dots show up on this map, right, as more jurisdictions adopt these policies. And then finally, right, things like resilience, decarbonization, electrification, right, those are kind of buzzwords we hear a lot, but the underpinnings for success for any of these efforts is still building efficiency, right? It makes no sense to, you know, install heat pumps into homes that are not insulated and air sealed, or it makes no sense to put an acre of solar panels around a commercial building that is an energy hog, right? Like efficiency is really the starting point for all of this. Right, so wrapping up, I think this is my last slide. Right, heating and cooling, right, as we talked about, we've covered a ton of ground, right, but heating and cooling are really the dominant energy uses in our buildings, both in US and Canada, residential and commercial, right, and really the envelope is critical, right? Even for big commercial buildings that have got a lot of energy use in the core, right, if we have a junky envelope, it's still going to be hard to make a lot of gains. Right, and again, for new construction, building to the latest codes or beyond, it's kind of the best, easiest solution. And again, retrofit solutions, right, really vary, right? We need to air seal and insulate where we can, improving our windows where we can, where it makes sense. Controls, thermostats are obvious ones. And it's just really important to remember that, you know, again, buildings are systems of systems. This rule applies no matter what. It's important to not forget that when we go off and want to make these changes, so that we don't end up with unintended consequences, maybe that we didn't want. And with that, I think I'm going to turn it back over to Natalie for a second before we do questions.
Thank you, JR. Yeah, before we get into some questions, I'd like to take a few minutes to go through some additional resources we have for you guys. First and foremost, we maintain all of our informational resources on an online portal called The Source. You can get to this via jm.com, or if you scan the QR code to the right, it will take you to this online page. This is where the webinar will be posted within the next few days, and you'll also have access to our other recorded webinars, blogs, product documents, trainings, and tools. Also, for additional resources, I encourage you all to follow us on our building installation social channels. We provide a wealth of informational resources on both of these. Finally, I would like to quickly highlight JM Tech Connect. The Tech Connect team is available to all JM customers. So whether you need help with installation, troubleshooting, parts and equipment, or even specifying questions, our experts are here to help. Finally, for anyone who attended today, you will receive a certificate of completion after the webinar that may be submitted for professional development hours. This will be sent to you via email and should be in your inbox by next week. Again, a recording of this webinar will be posted on the source within the next couple of days. When it becomes live, we'll send you a link for direct access. So if you miss any part of the presentation, if you would like to view the webinar a second time, or if the content might be relevant to a colleague, you'll be able to access it on demand. And with that, let's take it into some questions. We had a few come in. Let's begin with how long does it take to see a return on your investment when you invest in the energy saving measures you've outlined here for residential? How about commercial use cases? That kind of seems like a two-part series.
It kind of does. It's an excellent question, and it's one of those, you know, I have to give you the consultant's answer of it depends, right? It really depends on what the measure is, right, and how much that costs. So, you know, I would, and especially for commercial buildings, there's honestly been, there's been over the years, you know, the Department of Energy has got an organization called the Better Buildings Alliance. They have done tons of webinars and papers over the years, a lot of which I kind of dug into myself in preparing for this webinar. You know, so the payback depends. It can be very short, right? It can be, you know, less than a year, especially when it's things like, you know, what we call retro commissioning, you know, just kind of tweaking and upgrading and making the building operate the way it was originally designed to, right? So kind of going back to the control systems, a lot of times those paybacks can be quick because the investment is small, right? Conversely, right, if you're gonna like strip off all the windows and you know, and replace all the windows, like that might take a longer that might be a longer payback period just because the investment is much bigger. You know, I would say in terms of a passive measure, again, things like pipe insulation, right? It sounds like kind of boring, but you know, insulating all of your chilled water and steam lines in a commercial building, right? Making sure that those heated and cooled fluids are at the temperature you want them to be at the place where they're being delivered, can you know, again, small investment can have a real nice payback. So kind of a squishy answer, but it's kind of a big question. So hopefully that at least tax it and point you to some resources. Better Buildings Network is an awesome resource.
Next, we have when increasing wall insulation, R value, are improvements added?
Yeah, and I pulled up that question window too, so I'm seeing that. And so David, I think maybe what you're asking is like in that table that I showed, like the different R values I was showing in those tables for wall insulation, at least for homes, it was more, I guess, upgrades versus added, right? So it's more like insulating your wall with R19 instead of R13, if that makes sense, and then realizing those savings from making that substitution, I guess, is the better way to describe those versus an add.
Okay. Next, we have if you are in a heating dominant zone region, overall, is a black roof better than a white cool roof?
Yep, I saw that question too. That is an excellent point, and that is true. So, right, part of the other comment was, right, is kind of this white roofs are good for reducing cooling load, right, but they don't reduce your heating load. And this person makes an excellent point. I kind of, you know, glazed over that as I went through there, but that's very true. And so with commercial buildings, again, it really kind of depends on, right? It's not just the building, it's what are you doing in that building, right? So if you're, let's say a warehouse in Minnesota, and you need to, maintain that warehouse at kind of room temperatures even in the wintertime, a white roof is probably not your best choice, right? Because of that very thing. You do see a heating penalty from white roofs. One thing that I didn't really talk about much regarding white roofs, though, is they do also help with what's called the urban heat island effect, right? Which is just this phenomenon where, because our urban centers, right, have buildings and they tend to be paved with black asphalt, they are hotter, they are warmer, especially in the summertime, than the surrounding countryside. And one of the other benefits of white roofs that sometimes is even counter to energy savings is mitigating this heat island effect. And so we see, cities like Chicago, for example, or Denver, where I'm at, right, adopting these policies that are kind of requiring commercial buildings to have white roofs put on them, sometimes even at the expense, right, of a heating penalty. So excellent point. You're 100% correct. It really requires a digging in before you make those white versus dark roof decisions.
Okay, and it seems like we might have time for 2, maybe 3 more questions.
Okay.
Is there a tier system tied in with the new construction for commercial buildings pertaining to the new codes, similar to the Net Zero Ready for Residential 2030?
So yes, and based on the questioner, I'm guessing that's geared a little bit more towards Canada. And yes, the what is it? The National Energy Code for Buildings in Canada is the commercial building energy code up there. And yes, the 2020 and soon to be 2025 NECB, right, does include this tier 1 through tier 5 scheme for commercial buildings. And again, the idea is that as provinces or jurisdictions, right, adopt a higher tier, we are ratcheting the screws down tighter in terms of the expected efficiency of these of commercial buildings. So yes, there is a tier system. Off the top of my head, I can't tell you what the different tiers are, but I seem to recall like tier 2 is about 10% better than tier 1. I think 3 is about 30%. And kind of once we get down to tier 5, it's like, it might be like 60% better than tier 1. Like that's kind of the range. And so, again, the idea being from Canada's perspective, right, hitting to this, zero net energy, zero net emissions sort of targets, right, by, well, I don't know if it's 2030 or 2050, but, here within the next, few decades, hitting those targets. Good question.
Lastly, how do you quantify carbon emissions in buildings?
That's another good question. And really, right, this is where, we kind of take how our buildings use energy, and then we have to look at, what sort of energy do they receive, right? So obviously, if a building is using energy by directly combusting, right, things like natural gas, right? So think boilers, water heaters, furnaces, right? Then we can directly just calculate, right? That's a direct emission by the building itself. And so, the connections between just energy efficiency and reducing carbon emissions are obvious for those sorts of things. And that's where we see a lot of efforts towards electrification, right? Trying to replace direct combustion systems, right, with electric systems. Oh, excellent. Somebody put in an excellent comment about the Canadian tiered codes. Sorry. But then I would say when we talk about systems in buildings that are already electrified, right, then we have to kind of look back at the grid that we're connected to, right? So, and again, that just kind of depends, right? So if you're a commercial building here in Colorado, right, there's going to be a certain mix of renewables and coal-fired and natural gas, right, kind of sources that are feeding the electrical grid, right? If you're in Texas, it might be a little bit different. If you're in, Tennessee, it might be a little bit different. So that's where this sort of carbon accounting gets I mean, it's not hard, but it's just, there's this additional complexity. But certainly reducing carbon emissions, right, is 100% what's driving these electrification efforts that we see to varying degrees throughout the country.
Okay, thank you, Jared. And thank you very much to everyone who attended today. If you have any additional questions, please do not hesitate to reach out to us directly or via the survey that will pop up on your screen directly after the webinar. Otherwise, take care and enjoy the rest of your week.
Thanks, everybody.